Hello. Welcome to the Stats Workshop. Have you all managed to pick up one of the handouts from the back of the room? If not, it is essential that you do so. You may have noticed that on the board, thank you girls. You may have noticed that on the board I have written, have you completed the pre-workshop material on Canvas? If not, you must do it now. In order to make the most of your session today, you need to have completed the pre-workshop material. Now, some of you are looking at me blankly. The pre-workshop material that I am talking about is you need to watch the recordings on the mean, standard deviation and the standard error. You need to watch the video on correlation and regression, and then you need to have a calculator that is capable of calculating statistical functions and watch the video on how to calculate standard deviation using that calculator. Right, how many of you still need to be getting on with that? Come on, a bit of honesty here. A few of you? Right, what we're going to do is, I am going to give you a few minutes just to have a look at that. For those of you who have already done the pre-workshop material, you can start getting on with question one from your workshop material. Now, the whole purpose of these stats sessions is that we are adopting a flipped learning approach, which means you look at the workshop material before you come to the session. You use the session to complete the workshop material that we have with the questions here, so that you can get the most out of the session by asking me for help. Okay? If you have not completed the pre-workshop material, this won't work because you won't be able to complete the questions that are available to you in the workshop. So, first thing you need to do, complete the material. If you have forgotten what the videos have said because you watched it 2 weeks ago or whatever, then you need to go and have a look at that. I will go through on the visualizer how, I know it's cool, isn't it, how we are going to answer the questions. So I'll give you 10 minutes to have a go at answering question one. I'll come round and help you out as appropriate, but make sure, if you haven't done so already, you watch those videos to help you out. Right, let's have a look at question one. So, question one asks you, the graphs above show two data distributions. Which of these distributions is normal, and what characteristics did you use to define this normal distribution? So, hands up if you think B is normal. Hands up if you think A is normal. Hands up if you don't have a clue. Right, okay, just checking. So, we're all agreed that A is the normal distribution. Now, how did we all come to this conclusion? How did we all come to the conclusion that A was the normally distributed data? Yes, young man? So, you've got the fact that it's symmetrical. You've got the fact that it is a bell curve shape. Anything else? Excellent. 2 lovely points. Yes? The mean is in the middle of the curve. So it will be the sample mean, which is x bar, is in the middle of the curve, and the mode. So most of the middle values, so the mode will be in the middle of the curve. Anything else? That seems quite enough, really, doesn't it? Yeah, so there's quite a lot of things. So we already know it's basically the typical shape of most random experiments that you get when you're looking at data. And we will be using that to describe quite a lot of the next few questions. So if we look at question 2, You're doing a field survey on a swamp which is home for 5 million frogs. Yeah? So during the first month of your field trip, you measure the weights of 1,000 frogs and you find that they are normally distributed with a mean of 52 grams and a standard deviation of 10 grams, according to these sample statistics, and it asks you a few questions on that material. Right, over the next 10 minutes, I want you to work your way through question 2. Okay, so work your way through question 2, and we'll be coming around to help you out. If you get stuck, stick your hand up and we'll come around and help you out. Thank you. Right. Shall we go through some of the answers to question 2? Yes? Right, so approximately what proportion of the frog population in the swamp will weigh between 52 grams and 62 grams? So what is it trying to ask you? Okay, what answer did you get first of all? Anyone brave enough? Yes, sir. 31, close, but not quite. 34, yep, absolutely. So how did you come to get 34%? So you did 68% divided by 2, which is absolutely right. So if you go back to the first page, it will stop being fuzzy in a minute, it tells you, if we add our data to this, our mean value, x bar, equals 52 grams. Everyone in agreement? Yeah? This represents 1 standard deviation away from our mean value. Yes? So, what we want is everything between 52 grams and 62 grams, which is this here. Okay? Now, if you go to the bar and you pay £10 for 2 pints and they give you one pint, how many pounds do you want back? You pay £10 for 2 pints, they give you 1 pint, how many pounds do you expect that bartender to give you back? £5, brilliant. So, on the same line, if 68% of all your values falls within 1 standard deviation away from the mean, but you are only looking at everything from 52 grams to 62 grams, so you're looking at everything for the mean value plus 1 standard deviation, yeah? So, this is your 2 pints, you've only been given 1, so you need to half the amount that you're paying, don't you? So, effectively, 1 standard deviation away, you've got 1 standard deviation away from x bar equals 68% of all your values. Okay, so therefore, if you want x bar plus 1 standard deviation, you will need to do 68% divided by 2 equals 34%. Okay, so you are only actually interested in that section here. You're not interested in this value because 68% covers all of that, doesn't it? Okay, moving on. Then it asks you approximately what proportion of the frog population in the swamp will weigh between 62 grams and 72 grams. Let me help you out here. So, you've got your 52 grams, which is your x bar, yes? You've got 1 standard deviation away, which is your 62 grams, and 2 standard deviations away, which is 72 grams. Okay? How will you work out what proportion, So again, these are asking for proportions, not absolute numbers. What proportion of the frog population in the swamp will weigh between 62 grams and 72 grams? Anyone brave enough to give the answer? Yes, young lady. 13.5%. How did you arrive at that? Right, so basically you're absolutely right. You are using the knowledge, you've worked out that that is 34%, okay? So you need to work out, if you think about it as areas, you need to work out that bit, don't you? So you know that that area here, for example, so 2 standard deviations away from the mean, you know that 47.5% of your data will fall into that range, okay? You've already worked out that between 52 grams to 62 grams equals 34% of your data. So 95% of your data lies within 2 standard deviations from the mean. If your mean plus 2 standard deviations equals 95 divided by 2, same calculation as above, but we're using the values for 2 standard deviations, you're looking at 47.5% of the data. So 47.5% of the data there. Now, if x bar plus 1 standard deviation away from the mean equals 34%, you need to subtract that from that to get the value between 72 to 62 grams, 47.5, so this whole area here, minus 34 equals 13.5%. Okay? Right. And it goes on. Sorry about my handwriting, by the way. It's not brilliant. So on a later visit to the swamp, you set some frog traps and catch 500 frogs. On the basis of your previous sampling, how many of these might you expect to weigh more than 72 grams? So you go back to the swamp and you're a smart person and you think, oh, actually, I expect that a certain proportion will be above 72 grams. First thing you need to notice about this question is it is asking you for a number now. It's asking you how many. The previous questions have been asking you for a proportion, okay, so a percentage. Now it's asking you for an absolute value. Okay, so let's go back to our normal distribution here. Okay, so if 95% of our data falls within 2 standard deviations away from the mean, we are looking for that other 5% because we are trying to find all the values that would weigh more than 72 grams. Okay, why is it not 4%, you say? Well, actually, 99% of the data is within 3 standard deviations of the mean, but that's still only 99%, isn't it? You would expect that out of any sample, you would get 100% in total. Okay, so you've got to remember that although you cannot predict the exact value of that 1%, you will still have to add it into your calculations. So, how many frogs? How many frogs did you calculate? 10? Okay, you've got 10. 12.5? 13? Right. You're absolutely right. The answer is 13 because you can't sample half a frog. Okay? And I'll show you how I got there in a minute. But 10 is very close, and what you've probably done is you haven't You've probably done 4% as opposed to 5%, isn't it? Yeah? Have you looked at the remaining 4%? But you're very, very close. So, you need to look at the remaining 5% of your sample. Being greater than 2 standard deviations away from your mean value. Okay? So therefore, 2.5%, that's gutting, isn't it? Sorry, technical error. So 2.5% of your data is going to be greater than 72 grams. So 2.5% of your data you are expecting to be greater than 2 standard deviations away from your mean. Okay? So therefore, you say 2.5% times 500 equals 12.5 frogs. So young man at the front, you're absolutely right, equals 12.5 frogs, but you cannot sample half a frog in the same way that you cannot have half a girlfriend, okay? You either have the girlfriend or you do not. You either sample the frog or you do not. So, 13 frogs. Right. And then it goes on to ask you, what is the standard error mean for your sample of 1,000 frogs? Okay, so what is the standard error mean? So your standard deviation tells you how far your data is away from the mean. Okay? But what you need to think about is when you have your data, you can have your mean value here, okay? 1 standard deviation away either side. What is the difference between that graph and that graph? If it was the same area, I'm actually rubbish at drawing, so that can't be helped, okay? So if they were both the same area, what would the difference between those two graphs be? Same mean? Yes?
If the one that goes further up, would it be less samples?
No, same number of samples. Yeah? Yes? Less variation. What do you mean less variation? Right. So in the curve with the big spike, what's happened is more of the data is closer to the mean value, so it's less far away, so you don't get such a large range of values. In this one, the range is a lot bigger, okay? It's interesting that you said there might be less samples, because that's exactly what the standard error mean takes into account. So what might have happened is you might sample, for example, I am going to sample 3 people from this room to tell me whether or not people that study this brilliant stats workshop is mainly male or female. So I take my sample, 1, 2, 3, okay? So from that I deduce that 100% of everybody in this room is male. Is that correct? No. Okay, so on another day I take another sample. 1, 2, 3. So 100% of everybody in this room is now female, right? That's not correct either. So what that does is, it says, if on a third day I count 10 people, for example, so I might go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Already I'm getting a better view of what the proportion of the sexes in the room actually is, isn't it? Yeah? So the standard error mean takes that into account and says, this is the standard deviation, so this is the deviation from the mean, with respect to how many samples I actually took. Now, how does this actually work? So the standard error mean is your standard deviation divided by the square root of n. What's n? Sorry? Number of samples, yeah? So, in this case, it will be 10 divided by the square root of 1,000, which equals 0.316. Did everyone get there? Yeah? Okay, then it moves on. Ooh. You move on to the next swamp, which also has a population of 5 million frogs. So total population of 5 million frogs. When you do a similar survey here, you look at 1,000 frog with the mean weight of 48 grams and the standard deviation 9 grams. There's two possible explanations for the difference in mean weights, and that is A, the population of frogs in the second swamp does not grow quite as large as the first swamp, or B, the two populations have identical mean weights, but you have a small difference in the sample means due to the random sampling error. So A is saying that there is a genuine difference. B is saying, like when I was picking out what sex the people in the room are, it's just a sampling error. If I took more samples, I'd get a better idea of what the true value would be. Now, how do you work that out? First of all, you need to work out the standard error mean for the second population. So that equals 9 divided by 1,000 equals 0.285. Okay, so we've got two standard error means, the one for our second pool and the one for our first pool, which is still on the page there. Right, what you need to look at now is, I need some scrap paper. Okay, never mind. What you need to look at now is you're basically trying to find out, if this is your second pool with a mean weight of 48 grams, and you've got your first pool with a mean weight of 52, was it? Yeah? 52 grams. What you're trying to say, in population A, if the population of frogs in the second swamp does not grow quite as large as the population of frogs in the first swamp, it's basically saying that these populations are separate. So there is no overlap between the two populations. Okay? In the second scenario, the two populations have identical means, but you have a small difference in sampling means due to random error. So that's saying that the two populations, they're probably from the same, they're probably the same mean weight, but because of the way that I've sampled it, I've only looked at 1,000 frogs out of 5 million, that I've probably this is just an artifact of my sampling, so it's just because I've taken 1,000, I haven't looked at enough. In this case, there would be a subset within that population which could have values which could belong to either group 1, so pond 1 or pond B. Okay, but it would be the same value, so there will be an overlap. So what you need to look at is the maximum value for your standard error here. So you need to look at the maximum value, and you look at the minimum value for your standard error there, okay, for that graph. Is everyone with me so far? Okay, so if this value is not less than this value, basically there is no overlap. Okay? So let's have a look and see what these values actually are. So let's take pond 1 first. So the real mean equals the first mean, which is 52, minus, so 52 minus 3 times 0.316. So it's the mean minus 3 standard deviations away from my standard error mean, which takes into account how many samples I've taken. Okay? And that equals 52 minus 0.948, which equals 51.052. Okay? We're still on the page, yes. Right, for this one, your real mean, we are looking for the maximum value now, aren't we? So we want x bar 2, so this one, we want plus 3 times 0.285, so that's 48 plus 0.855. Please correct me if my calculations aren't correct. And that equals 48.855. Now, 48.855 is not bigger than 51.052, is it? No? So therefore, these populations are genuinely different. Okay? Right. So if we move on to the next question. Question 3, you have a lot of data here. It is quite important that you have watched that video on how to use your calculator to input statistical values to work out your standard deviation. Because if you do not watch that video, what we are expecting you to do today is work it out by hand, which is like that. Okay? So I suggest that if you have not watched that video, you need to watch it on your phone, so go onto Canvas and watch it on your phone so that you can answer this question, question 3, on our caterpillar data. Okay? So I'll give you 10 minutes to have a look at that. Off you go. So quite a few of you have come on to plotting the graph for question 3. Don't forget your independent variable always goes on the x-axis and your dependent variable always goes on the y-axis. So what is your independent variable? What does that actually mean, guys? Not the one you control. Right, you can't control and change something, but which one is it? The one you change. So the thing that you are changing is your independent variable. In your sample, what are you changing? Time. So you are choosing what time to take the samples at, and the dependent variable is the thing that you are measuring, absolutely. So the thing that you are measuring is the weight of your lovely caterpillars. So don't forget, independent variable x-axis and dependent variable y-axis, and then it's just a case of the old along the corridor and up the stairs to plot your data points. Should we have a go through question 3? Okay, so 20 newly emerged caterpillars were labelled and held in a vivarium with free access to water and food. Their growth was monitored by weighing each caterpillar at weekly intervals over a period of 10 weeks. The table below shows the recorded weight of each caterpillar at each weighing. Okay, the data from each caterpillar weighed in grams is shown in a separate row, and the data recorded each week are shown in successive columns. So you need to select 5 caterpillars and draw a graph to show the relationship between the time and the weight for each caterpillar. Now I've been a bit naughty, and if I'm honest, I've only actually just drawn 1. But you should have, can I make this? You should have your time in weeks along the bottom and your weight in grams on the y-axis. Okay, with your various 5 caterpillars with appropriate axes. So you want each square to represent the same amount on each of the axes, and you want your actual units in there too. Okay, and then it goes and asks you, in graph 2, show the relationship between time and the mean weight for all the caterpillars. So what do you need to plot together in graph 2 to get that information? What do you need to plot? Sorry? Anyone, what did you plot? At the back. The time and the mean weight, you're absolutely right. So don't go and plot 20 caterpillars. You want to plot the time on the bottom and the mean weight of your caterpillars along the side. And then it asks you, if we want to illustrate on graph 2 the variability in growth between caterpillars that we can see in graph 1, how can we do that? So if we want to see at each week how much variability around the mean, so what the spread of the data is around the mean, what would you plot on each of these? What would you need to add? Yes? Standard error, not standard? Standard deviation, yeah? So you would need to plot an error bar with standard deviations on each of your mean weights. And then it asks you, if we want to show on graph 2 how reliable our mean plot of growth rate is as an indicator of the growth of the caterpillars, i.e. the real mean, and then we go back to plot the standard error as the different bars. So just as an example, this graph 2a shows you the plot with the standard deviation plotted, and 2b shows you the same graph but with the standard error plotted, and you can see that the standard error is a lot tighter to the mean compared to your standard deviation. And then after that, is that all the questions for that? We're on to question 4 now. So question 4, tabulated below are average body and brain weights for several animal species. Is a correlation between the two variables, body weight and brain weight, readily apparent from the tabulated data? And that's where your starting point is before you go into looking at correlations. So I'll just give you a few minutes to get on with that. So 5 minutes just to get on with question 4. So let's just quickly go through some of the theory for question 4. Okay, so you've got the weights, the body weights and the brain weights in the table, and it asks you, is a correlation between the two variables, body weight and brain weight, readily apparent from the tabulated data? Hands up if you said yes. Okay, hands up if you said no. Okay, would anyone from the no side and the yes side like to explain why they said yes and why they said no? Go on then.
I said no, because if you just look at it as it is, it's not organised very well, so you can't tell just looking at it.
Lack of organisation, if you just look at it, you can't tell exactly what's going on, isn't it?
From body weight lowest to biggest, you might be able to see correlation, but you can't as it is.
Right, so if you organised it a bit better and put the table in ascending body weight or something like that, then you would be able to get a lot more information from it. So as it stands, the table as it is, you will probably, it's not particularly useful to you, okay? So you probably will find that it's not that useful. And then the next question asks you to plot a graph of the data, to see whether there is a relationship between these two variables. And for this data, it tells you that r squared is 0.9205 and y equals 1.02x plus 37. So who remembers the equation for a line? Yes? Y equals mx plus c, where m is the gradient and c is the y-intercept. Okay, so you've got that equation there, haven't you? Y equals mx plus c, and it asks you to draw the regression line on your graph. Is it positive or negative, and how strong is this correlation? So this is my attempt at drawing a graph. I've got the body weight on the bottom because you've chosen the animals knowing full well that a rat is not going to be as big as a cow, okay? So you've chosen the body weights and you've measured the brain weight to see if there's any correlation. Now, is that a positive correlation, a negative correlation, or is there no correlation at all? Positive correlation, excellent. So, positive correlation, that answers that. How strong is the correlation that you derive from this linear regression plot? So how strong is this correlation? Anyone from over this side of the room? Yes? It's a strong correlation. How strong? Sorry? It's quite strong. Can anyone put a figure on this? You're absolutely right. It's quite strong. Not 99, 92%. So basically, you have been given your R squared value. So if you look at this, you have already been given your R squared value, which is 0.92. Now what that actually tells you is that 92% of all of your data can be described by your line when you say y equals 1.02x plus 37. So 97% of your data fits in with that equation, okay? Which means that 8% of your data remains completely unexplained. So this might be one of your 8%, for example. It's somewhere random. It's not on the line. And regression, what that looks at is it asks, if you've watched the video, how many of you have watched that regression video? Yeah, quite a lot of you, so a big proportion. It asks on a regression, if there's no correlation, your R value is close to 0. If it's close to +1, it means there's a positive correlation. The closer it is to 1, the stronger the correlation. If it's close to -1, it means there's a negative correlation. Right, the reason why we've only given you an R squared value for your statistical analysis is because if you look up how to work out R, it's actually a really complicated formula which you do not need to know for the test. Okay, so there's no point working out how you actually work out the R value. You just need to know that R squared shows you the percentage variance of the experiment that can be explained by a trend line. So R squared shows you how far away your points are from your trend line, okay? So is your plot useful for inferring the brain weight of other species from their body weights? For example, what brain size would you predict for a jaguar with a mean body weight of 157? So how would you do that? You would say mean body weight of 100 and, hang on, 1, 2, 3, 4, 5, 157 would be about 200, right? Yeah? Did everyone get something like that? Yeah? So it would be about, you'd expect it. So if you go 157 this way, along the corridor, up the stairs, you get to about 200 grams. That's how much you'd predict the brain size to be. Well, in actuality, a jaguar's brain is more like 100 grams, but it's a good reference point to start with, isn't it? Yeah, so the jaguar must be one of those ones that doesn't quite fit. Okay, so the last question. Tabulated below are the scores on a dexterity test taken by a student after consuming alcoholic drinks. So the number of drinks is noted and the score on the dexterity test. Plot a graph of the data to see whether there is a relationship between these two variables, and how would you describe this correlation? We'll go through this question in about 5 minutes. So plot the graph. How would you describe this relationship? Let's go through the final question. Thank you, nice and quickly. Let's go through the final question. I'm not going to talk over you guys. Thank you. So, tabulate below the scores on the dexterity test. Plot the graph of the data to see whether there is a relationship between these two variables. If you plot the graph, it should look something like this. Okay? Is there a relationship between the variables, and how would you describe the correlation? So how would you describe the correlation? Yes? Negative correlation? Yeah, okay. So, as the participant has more drinks, the score on the dexterity test decreases. Yeah, so that's what a negative correlation actually means. Is everyone happy with where that came from? Okay. I think we have reached the end of the session. So once you have completed those things, make sure that you have signed in for the session. And if you're happy with all the maths content and you've completed the work, I am happy for you to go.